All right, everybody, how we doing? Doing good. Woo! All right, I know it's coming that time of the year. It's April 1st. It's a joke that everyone's like, "Hey, let's just pretend not to come to class." April Fools. I'm playing now. I forgot it was April Fools. I got fooled by a few things. Oh, salary raises are coming. I'm playing now. I'm playing now. What else came today? It's Apple's birthday today, 50th Apple. What else is happening? Mario movie's coming out. Anyways, let's go back to here. Is my video thing. So, how you guys doing in Dr. Morris's class? Doing good? Um, let's see. Spring break, Laplace, Z's. Today is the first, so this is what we're gonna be talking about today. But Dr. Morris is like, hey, let's rush them because I think we're gonna be more focused on state spaces because I think he's more a state space person than he is a block diagram guy. Okay, that makes sense. So I'm gonna just briefly go over Z transforms, maybe clean up on. I'll think about what I want to do today, but I want to tack this assignment, computer assignment 6. Right? Has anyone looked into this one? Not yet. We're still working on the next one that's due this Friday. Right? Let's look at it because I don't want to go over this one. I already went over last class. Yeah, we literally derived everything. We got the answer right. Remember from last class? Not that hard. And then we put the transfer function right there, right? And then we got the Bode plots, or not Bode plots, frequency responses, right? Let's just run it again. Solutions. Get rid of them. Here's my Laplace transform plotter. Let me see. What was I doing? Let me see. Oh, this is my calculator. Let me see. Where is C4A? No, it's the wrong one. Let's see. What did I do? Lecture 7. There we go. Oh, yeah, and I gave you guys this. Do you guys like that I actually gave you guys material? PDFs, .MATLAB code. Did I copy my MATLAB? I think, yes, I did. I uploaded it because everything I do is uploaded, so you guys have fun. Let's see. What did I run? Control Enter. You guys like Control Enter? It's your favorite button. Why does it look weird on my end? There we go. System planes, right? Not that bad. I invented the poles to be stable. Remember all that stuff? We made poles, right? Cool. Kicking boxes, right? We were kicking stuff and just watching things go. Why is it generating like that? See? Cool. Not that bad. This can be modeled like, for example, what response or what circuit does this kind of response? Remember from the last class? Current going through a capacitor an RC capacitor, right? And you just turn on the system. Current is instantaneous and then decays, right? Because over time the capacitor acts like an open, right? So see, and then I'll show you guys my special lecture tomorrow for my 320 lab students. Yeah, signals and systems in the labs. Okay. Maybe I'll generate this plot too tomorrow. I'll think about it in real life. This stuff is good. It's all cool. Everything I try to show you guys, you can implement it in real life. Someone was asking me, like, I want to do this. It sounds so cool. Kicker boxes, residues. What is this? What did we run last time? Let me just run this. The heck? Oh, I remember what was going on. I was trying to do a different one. I was trying to simulate the poles of what's his name? What did I do here? H. Where's H coming from? H is this, and then my num is this. This. Oh, there's a gain term. Okay, this is where I left off the last time. But let me see. I don't think you need to worry about this. S real, sigma, omega, S real, size S, my num, my den. Let me see. Give me a second, y'all. Let me see. I don't know why that did not pop up, but anyways. You see that stuff right there, right? Remember that from the last class? Laplace transforms? What's this axis over here? Power? Let me see. 20 log 10 absolute value of your, what do you call it, transfer function, right? Power. And then, is there a way to do, let me see. If I were to do like, what do you call it, logs, like, you know, like log x and log y, like do, what do you call it? Instead of it being linear, right? Frequency going 1, 2, 3, 4, 5, right? It's going to go from 0.1, 0.10, or 0.1, 1, 10, 100, like log. If I were to do that, I'm not going to do that. You'll see that, oh, it starts looking more like you know, Bode plots, right? You see these nice, like what do you call it, slopes. They go up and down, and you can do some crazy stuff. But I think, you know what? Let's continue on with assignment 5 because I'm getting paranoid if someone doesn't understand what I'm talking about. Frequency response. Does that trigger anything in anybody? Like tomorrow's lab, right? Frequency response, right? I know you're smiling. Like, let me see. Use the freaks function, okay? Freqs. Freaks or frex. It's freak S. So like the frequency response in terms of S domains, okay? Calculate the frequency response, okay? Plot late. Personally, I would use semi-log because this is what I wanted to show you guys. Let me see. Omega. Omega is our play term. Let me do this, okay? Did I define W? Let me see. How do I check if I defined it? Go here. Did I define W? Not really. So I can use that. W, right? Omega, right? From minus 10 to 10, right? And then let me just do a precision right here. I don't know. 0.1. Actually, no. I'm just 0.1, whatever. Okay. Sounds good. Plot the magnitude response in dB. See, I edited these assignments. Let me show you what I did last year. Wait, wrong assignment. There we go. I cleaned these up, but Dr. Morris used the other one. You see, look, 0 to 100, right? You see what I'm supposed to, why I edited these assignments? And then I said, use semi-log x, correct? Title, x label, y label, log 10. You should generate 2 plots on one page. Note that this plot should be a slice of example 1, right? Let me, you know, I'll teach by example. Get rid of that. Thinking. What did I do last time? Let me see. Freaks. H, J, omega, don't blank out, Dave. I know, I'm tired too. Let me see. Because all I want to do is just get this transfer function right here, okay? And all I'm going to do is just sweep it. So let me see. Oh. Sometimes if you blank out, you can do the following. FQ freak S MATLAB. There you go. Because I think there's an easier way to do it. Let me show you. There you go. See? I'm blanking out. Okay? I'm going to do H omega, something like that, is equal to freaks B. Okay, what's my B? My num, my den, right? My num, my den. Does everyone understand what's going on? And W, right? That's our play variable, right? We're sweeping around. We're having fun. Okay? You know what? I'm not going to do the assignment. There you go. There you go. I'm going to do my assignment. Anyways, so that's that. But now we got to do this. Figure, I don't know, 1, 2, 3. semi log x. Is that how I want to do it? Yeah, semi log x. W, and then h omega. There we go. But then this needs to be absolute value, okay? So absolute value, correct? Right? Absolute value, right? So you guys understand when I'm saying absolute value? We're just making all the complex numbers turn, boom, it's gone, right? We're just making it nice to plot because we can't plot imaginary unless you want to. But now we got to convert it to power. So 20 log. Is everyone understand what I'm trying to do? 20 times log 10 of this. Is that understood? Right? Easy stuff. And then x label angular frequency. Then I'm going to do $sign omega $sign interpreter latex. Why? Because I want to show you guys the funny omega. Y label power in dB. Boom. Cool. Run it. I love it. I love it a lot. And it can be a lot better. Let me see. 0.1. What does that look like? Filters, right? Bodie plots. Let me go one more 1,000. Is that cool with everybody? Let me show you something cool. Let me see. If I go here, right? 40 dB. Yeah, close right there, or 40 decibels. Is that cool? There we go. Do you see how the difference between this right here and this right here is about minus 20 dB, right? And then in terms of frequency, it's off by a decade, correct? Who's in my Monday labs? Remember this? Remember how I was talking about it in the class at 20 dB slope, right? So now you guys have the signals and systems stuff, okay? So I taught in the lab the electronics version, right? Now I'm teaching you guys the signal processing stuff. So now you can do RF circuits. Are you understanding what's going on? Yeah, it's pretty cool, right? 20 dB per decade. And then what's this right here? Well, you guys wouldn't know unless you go into control theory. Like Q peaking, right? Resonance, right? So if I had a frequency, if I threw noise at this, right? The thing that's going to cry the loudest is going to be this right here. It's going to produce a tone at, what's the frequency? 6.7? Like 6.7, which is close to, let me see, right there. 7, right? Where's that number coming from? Now let me use a practical one. Is that cool? Who wants to see me change things? Watch this. 20. I don't think I like that one. Let me see. 20. And let's just see what happens. Come on. There it is. You see where it is right now? 20. Everyone understanding what's going on? Everyone can do this at home? All right, I'm going to copy and paste this exact code, and it's not the right answer because I want you guys changing it, okay? Copy, paste with a purpose, wink, wink. Okay, is this valuable information? All right, good stuff to get you guys done with assignment 5, or is this assignment 5? Let me see. Let's go to the official website. I don't want to play anything crazy, okay? Dr. Morris's website, right? Assignment due this Friday, right? Click on that. But I think the assignment is asking you for minus 10 to 10, right? Right? But he's not even making you do power, okay? Actually, funny enough, do you see that right there? Here's my problem. Decibels, right? Needs 20 log 10. But he forgot, or you see, plot the magnitude in dB. So it's assuming that you guys need to know this, okay? That's why I edited the assignments with Dr. Stever, because I want you guys knowing what's going on, right? And you see how he uses plot instead of semi-log x. You guys understanding what's going on now? Is that cool? X label, Y label, subplot, Y, generate two plots. Oh, because you need the phase. You guys excited? Watch this. Plot 1. Subplot, we need 2 rows of with 1 column in position 1, okay? And then I'm going to do subplot 2 rows, 1 column in the second position, semi-log x omega, and then it's the angle. So you know what I'm going to do? Angle, what do you call it? H omega? There we go. Think that should work? Let's see what happens. And then I'm going to copy this. Boom, copy, paste. And then this is not power, this is angle. But I think, let's just run this. Whoa, looks cool, huh? But this is in radians. Who likes radians? I don't. Or I like degrees. Circular, 360 degrees. How would I convert this to degrees? So it's in radians, right? So I got to divide it out by radians, right? So pi, right? So divide by pi, right? Correct? But now I need to multiply. So for every pi, I get 180 degrees, right? So if I multiply this by, I'm going to do it right here, 180, right? Is that cool? Now let's do this again. There you go. A language we all understand. And you see this right here, right? 74 degrees down to whoosh, minus 86. What's that difference? Actually, that's a good question. 74 minus 86, so 74 plus 86, 160. Yeah, close enough. About 180 degrees, kind of phase change. You'll learn this more in DSP when you learn about how zeros, or is it zeros? No, it's poles. Poles change frequencies. They jump from place to place. You'll see, like, if you play with LT Spice, you'll see like these jumps in frequencies or these like drastic changes. Usually poles affect the phase response. And funny enough, that's what I want to propose for my PhD, is a lot of people are going crazy for magnitude responses, right? Because magnitude is like, think of it like food. It's like money. It's like, boom, it's great, right? But my proposal is like, I think the phase response matters a lot more. And a lot of people ignore it. Dr. Baker did, and he was like, there's something there. Because he talks about gain margin and phase margin, because gain margin is more important than phase margin. But the phase response personally, and that's what I want to do my research on, I think it matters a lot. And I want to research that for my PhD. So personally, as an undergrad, this looks like a filter, right? That looks like, whoa, go into your lab, resonance, cool. And then you guys look at this stuff right here, like, whoa, what the heck is that, right? Right? As an undergrad, is that correct? Like, look at this. Let me run it again. You see this plot right there? What does it mean? Well, there's a phase change, right? But it doesn't mean too much because you're more focused about just getting out of here and passing the class, right? So for me, like, as an undergrad, after this class, this looks cool. This is a filter, right? Control system theory, build a circuit in the labs. But this right here, like, I think it's important. Anyways, I'm going on a tangent. And then use the roots function, use the TF to ZP, Z-plane, residue function, the convolution function. That's easy stuff, right? Okay, I don't have to go over it. Is that cool? All right, let's go to our next topic because I don't want to waste time there. Let me back out of here, okay? And now let me go to Z transforms, okay? This is what I'm going to be talking about today, okay? Computer assignment 6, right? You guys remember Z transforms? What do you guys know about Z transforms?
They're kind of similar to Gauss transforms.
Kind of, yeah.
But for our poles, it's kind of centered at 0. We use the unit circle to determine whether or not it's causal.
Yeah. It's for digital systems, right? That makes sense. So, in short terms, let's just say analog can be sampled and you can go digital, right? And when there's an analog version, there's got to be a digital version that mimics it. So all these S's, well, what's S equal to, right? It's equal to some attenuation coefficient. We call it sigma plus j omega, right? Is that cool? It's got an angular frequency. Is that cool? Something similar when this is analog, but digital, right? Okay. We actually go into the Z domain, right? Which is equal to e to the, this is where I blank out.
It's R times e to the j omega.
Kind of, yeah. Is that good with everybody? What's his name? Because let me tell you this. I'll give you guys the cheat sheet. So remember how every analog signal in the whole universe, okay, or maybe depends. Every analog signal x of t, right, is composed of an amplitude, right, some exponential, right, because Euler's equation. What's it call it? Let's see. What do I want to do? Just put an alpha t. Is that correct? Is that good with everybody? EDDST. I guess, yeah, let's go with that. It's going to have some magnitude and then some what do you call it? Some phase, or I don't want to say this is phase, but it's composed of this, okay? Is that understood with everybody? So with digital signals, okay, x of n, right? We're going to have some amplitude, correct? But then we're going to have some residue here, okay? I'll just call it r, okay? And then it's going to be to the function of n or something like that. And then let's put the u of t right there, u of n. All right, is that cool with everybody? It's got a magnitude, and then there's something in here that's doing something crazy, right? Is that cool? Oh, sorry. Thank you. Let me know when that happens. Okay? And then this right here can be complex. It's a pole, or actually, let me just get to the surprise. But you start realizing that this right here is like related to, what do you call it? Related to the pole. Right? Same thing with this guy right here. Okay? Make sense? Okay? And then let me just talk about the circle, okay? How is he talking about the circle? Did you guys go over the region of convergence again? No, not yet?
I don't think so. I really introduced it, but I think it's the fact that as long as the region convergence goes outside the circle, it's causal.
Let me see. Give me a second. So let me just, this is the imaginary, and this is the real, and I'm talking about S, okay? Is that cool? This is the Laplace transform, LT, Laplace transforms, right? So the way that, I don't know if, this is how Dr. Stubru taught me. So let's say, okay, everyone agrees right here, this is, if there's a pole right here, it's stable, right? If there's a pole in this area, it's stable. Right?
In terms of Laplace, it's only stable if it includes the imaginary axis.
Oh, you're not wrong there. Sorry. So let me go explain. If I were to put a pole right here, right, and if I drew this line right here, right, and then if I drew another, let me see, let me use another marker. I love markers. If I drew this as my like region of convergence, right? Now it's a stable because we have this whole plot, okay? Okay, so let me just translate this. If you want a stable pole or you want a stable system, put your poles here, right? Because then if you go to the right side, it includes, that ROC includes that imaginary axis. Is that understood with everybody? Okay, so I'm going to use this yellow. I'm going to use this baby blue. And I'm going to use this, I'll use this black, okay? So let's just say I got this right here, and for some reason I took this circle and I enclosed it on itself like this. So I have the positive frequencies going up here, and the negative frequencies going down this way. But in digital systems, a positive frequency, if it goes too fast, can look like a negative frequency. So it's like you go around the circle, and you're back to where you are, DC. Okay. So the theory is if I just go back like this, okay, and I encircle everything, I can get the following. Now, let me just, and then you know what? I'm going to use this blue marker right here to show my point. Okay, is that cool? And then this right here is my Z domain. Okay, is that cool with everybody? So what I'm trying to say is, you see this blue region that I shaded right here? That's the inside of this circle right here, right? And then this yellow part, well, not yellow, but point is if you put a pole in here and it's a right-sided function, it'll be stable. So let me show you. If I put a pole right here, right, just a pole, and then if I draw a region of convergence, which like this, it's a bad region of convergence, and I go outside like this, right? This is my ROC for the digital system. It's stable. Why? Because it includes this imaginary axis. Imaginary axis. Is that cool with everybody? Everyone understanding what I'm trying to explain in a way without like going too deep into the material?
Is the blue circle, is the magnitude of that one?
Yes, it is. And basically, if you wanted to do a poll, let me see if I were to do the following. Let me think. Because this right here, give me a second. I'm thinking about it. Well, this poll is going to have some type of, they call it, value r, some distance, and then e to the j angle. Do I want to do this omega or something? I'll just put that right there. Is that cool with everybody? So like I can have these poles just dancing around. So now the question is, what about conjugate poles? Let me see. Let me think about this, because this right here is the real axis right here, and then if I have a pole over here, because let me remember, this is where I'm blanking out for a second, is conjugate poles, right? Remember how we were talking about that for the S domain? Let's just say if I put a pole, because I don't want to confuse anybody by saying, hey, if I put a pole right here, right? Let me put a pole right there, right? And if I draw that region of convergence going outside, right, it's not stable if it's a right-sided function. But if it's a left-sided function, if I go the other way, it is stable, but only when we go backwards in time, right? Understood? Okay, I'm getting some blank places. It's okay. A lot of our systems are usually dealt with going forward in time, right? So like if I put a pole here, and if I go forward in time, so what do you call it? It's always a right-sided function, right? It's causal, right? So that's what I'm trying to talk to you. It's a causal stable system, right? We like causal, right? Because it goes forward in time, and we like stable because it doesn't break. What about non-causal? That's a left-sided function, right? And what about unstable? Well, it doesn't include the actual axis. Does that make sense? Is that cool with everybody? Any questions? So yeah, this pole is unstable because if we're a right-sided function, it's going to be unstable. But if it's left-sided, it's stable. But only if we go backwards in time. Cool. Let me see. Now this is what I was trying to talk about, and I just remembered what I was doing. If I put a pole here, okay, right? It can't exist by itself. It needs to exist with a conjugate pair, pole 1 and pole 1 star, right? Everyone understanding what I'm trying to say? is you can't have something here without its conjugate pair. All right, everything comes in pairs. Does that make sense? Okay. Anyways, you know what? I think I'd teach better with like showing examples. Page 2. Let's see what your assignment's all about, because I don't remember either. Signal processing. There it is. That's not right. That should be a Z. Let me see. It's funny enough. If you were here like 10 years ago, the seniors at that time would be like, the difference between assignment 5 and assignment 6. Well, super rude. Is just change all the S's to Z's, and it's the same copy paste assignment. So basically, if you did 5, you already did 6. You just got to change the Z's. Okay, that's S's to Z's. So if I'm boring you, it's okay. If I'm not, if you're shook, So yeah, remember this right here? Polyval, right? We're going to evaluate stuff. Is that cool? And then this right here is only to make everything equal length, okay? The polynomials, or not the polynomials, just, what do you call it? I'll show by example. Let me see. The equal length functions equalize the order of the numerator and denominator to have the same form. Let's see, He doesn't give you an example. Great. And by him, anyways. Yeah, it's literally a copy-paste assignment. That's where I'm just like wondering if we're going to do this. But anyways, this is the one you guys want, huh? I'm going to write on another piece of paper, and then I think I'm going to just wrap it there. Or maybe I'll give you guys a treat. Okay, I'm just writing down the example, okay? Wrong marker. Y of n 2r cosine omega naught y n minus 1. Oh, I gotta teach you that too, darn it. 2y n minus 2 is equal to x of n, sorry, give me a second, minus r cosine omega naught x of n minus 1, okay? So I wrote this, but I forgot there's one last thing I need to show you before we start attacking this problem. Is, what do you call it? Solving responses, or not responses, but what do you call it? Transfer functions. Okay, for digital systems, okay? So remember, let's just say I have some y of n, right? It's just existing on its own, right? If I were to take a little z transform, right, z domain of this guy, it should give me this right here, right? Is that cool? And then what if I have y n minus 1? If I have a delay, z, and then it's going to be multiplied by z to the minus 1, right? Is that cool? And then let me see, because I don't know if he does this. I really don't. Dr. Subaru did, so that's how vicious he was. If you did, what's it called? A unilateral ZT, right? Is you're going to have these conditions. Let me remember. I'm just going to write this right here. Y of n is equal to 0. I think that's what it is. I'm not so sure. I don't want to go too deep. Unilateral Z transform formula, formula, whatever. There we go. I think this is it. Question mark. Yeah, I don't think people want to teach this. Yeah, I would teach it like this. This is easier. Just squares. But let me see. Z minus 1, Z minus 2. Okay, let me just translate this for you. I'm not gonna show that. Scratch this. Okay, less work for you guys. If I were to do n minus 2, right? Y, z minus 1 or 2. Easy, right? Any questions is going to be on your exam, right? Memorize this. And if you were Dr. Steve's student, you would memorize, well, whatever these conditions were. Yeah, he threw that question in there. So, wait, random question. Did Dr. Morris teach you guys unilateral Laplace transforms? Yes? Oh, okay, you guys did. So you had those weird initial conditions, right? Right? Okay, is he making you guys do the unilateral Z transform?
We didn't get to that
Oh, okay.
because he just introduced it like on Tuesday.
Okay. So there are going to be some conditions you guys got to memorize, right? Anyways, we're trying to do your homework. 3. This is 3. You guys like that I number my things? 4. Okay. And why is my camera like this? Well, there you go. Much better. Okay. So what's step 1? See that right there? Right? We're going to take the Z transforms, right? So I'm going to do the following. Y, Z, right? Is that cool? Minus whatever this right here is, 2R cosine omega naught. Let me see. Oh, I think I forgot the plus. Let me see. Give me a second, y'all. Ba-ba-bum. It was plus, okay. Plus, okay. I'm going to do the following. Z minus 1, right? Y, Z, right? Then plus R squared. Z minus 2, right? Y, Z. Cool. Is equal to X, Z, right? Just taking Z transforms. Minus R cosine omega naught Z minus 1 X of Z. I don't like sharing spaces like this. Actually, no. Wish it fit. Is that cool with everybody? What's the next step we do, or next thing we do? Combine like terms. YZ 1 minus 2R cosine omega naught Z minus 1 plus R squared Z minus 2 is equal to X Z 1 minus R cosine omega naught Z minus 1. Right? You guys remember that what a transfer function was? HZ is equal to Y Z over X Z. Right? Remember that? And then let's combine things. This goes here, this goes here. 1 minus R cosine omega naught Z minus 1 all over 1 minus 2R cosine omega naught Z minus 1 plus R squared Z minus 2. Boom. Answer to number 1. Any questions about that? Yes, no, maybe? Because I wonder if I should show you this other way, but I'm kind of afraid if I show you, you guys are going to be like, whoa, why don't we just do it the cooler way? Using Euler's equation. Who wants me to do that? Okay, get your money's worth. There's a way to convert this cosine into an omega or Euler, right? And then we can start splitting things and make things look a lot cleaner, cooler, right? Here's my rainbow paper. See all the dots? Because that also gets on the table, okay? I don't want to make a mess. So I'm going to do the following. So remember what cosine omega naught, right? How do I turn it to like using Euler's equations or exponentials? It's going to be e to the positive j omega naught, right? Positive frequency, right? Is it minus? Plus, okay, sorry. Plus e to the minus j omega, see? And then all this over 2. Is that cool with everybody? So I'm going to replace all these cosines with this. So it's going to get messy. Hz is equal to 1 minus r, what do you call it? E plus j omega plus e minus j omega. Does the dot matter? I don't think it does. And then all over 2. Then z minus 1. Is that cool? And then 1 minus, and then you see how this 2 kind of disappears, right? When I put this cosine right here, you see that 2 right there? So I'm going to do the following. R e plus j omega plus e minus j omega right there. R, yep, z minus 1, okay, plus r squared z minus 2. Is that cool? Because you can do something really, really cool with this bottom part right here, okay? Is you can start pole splitting, or you can get the poles, all right? So I can get 2 following equations, all right? What's the one thing these two have, or how to call it? I'm gonna, what's that thing called? Like, I'm trying to factor out things. Yeah, not common denominator, but it's like factoring out. Kind of. You see how there's z2 right here, or r squared, and this z minus 2 is right here, right? So both of these are going to share like an r. I'm just going to put an r right there, okay? Because if I multiply r times r, I get r squared, right? Right? And then I have a minus here. Let me see. I have a minus, and then I have a plus. So there's going to be a minus here, okay? And then let me see. They both share 1, okay? I'm trying to get I'm factoring things out, okay? Let me see. R, and then does anyone bothered if I do the following? E to the, what do you call it? Oh, it might be as simple as this. Is that cool with everybody? 1 times 1 gives me 1. This times this gives me this right here, right? And then this right here, and well, plus. This right here is the positive frequency. This right here is the negative frequency. Boom, right? And they share R. Is that cool with everybody? At the poles? And then what about here? Well, we can't really do anything there unless you want me to. Let's do it. 1 minus, because this right here, 1 minus RE plus J omega, 1 minus RE minus J omega. Does that make sense? Right there? And then R over 2. Oh, I forgot the Z. Is that cool? And then I forgot the Z right here. Z minus 1. Z minus 1. I don't like messy work. What do you call it? Z minus 1 RE positive J omega. 1 minus Z minus 1 RE to the minus J omega. And then this right here is 1 minus R over 2 Z minus 1 E to the positive J omega minus E to the minus J omega. Any questions about that? So here's your pole right here. Or actually, if I were to do your pole. Has he taught you how to get the poles? No? Is that you'll realize that this right here is the pole one right here, pole 1 right there. And this right here is pole 2, right? But pole 2 is equal to complex conjugate of pole 1. Any questions about that? And then, well, this right here, well, this is just your 0. Let me see. Because you can't split this. It's not a square. It's just 1. This is a value. This is a value. Oh, let me see. Is this going to matter? 0, 0. I think...
Could you multiply z?
Oh, you want to have positive z's? Is that what you're saying? Is that what you're saying?
Like on the numerator, couldn't we just multiply z so that I could get rid of the z minus 1?
Yeah, like, because if you multiply by z right here, you have to multiply by z here too, right? But actually, you need to do it twice. You want me to show you that? Because I think I'm waking up right now. Right? I have 2 z's down here and I have 2 z's up here, right? I'm going to use 1 z to get rid of this guy and it's going to go here. I'm going to use the other z to go right here, right? But consequently, I have these 2 z's that just hang out and do something funny. Right? Does that make sense? I'm going to redo this, not redo it, but I'm going to rewrite it in a form that's a little more clear. Okay? So if anyone's bothered by it, I think this should make a lot more sense, especially if you go into my DSP classes or Dr. Steve or Dr. Morris classes. Let's see, like this. H, z is equal to, I'm going to do the bottom, okay? Z minus R E J omega. Does this look cleaner? Does this make more sense? Right? Z minus R e to the minus j omega. Right? Cool? Everyone understanding what's going on? And then we have this z right here. So it's going to get rid of this, but multiply this by... I'm seeing things. Okay. R2 z... no. I remember this. Okay, I'm awake. I'm awake, everybody. Oh, whoops, sorry. There we go. You see this right here? And this is very important because this got me as an undergrad too. You see this z squared and this z, right? But there's no other like 0 term or constant term right here. So I'm going to rewrite this as z times z minus r over 2 e plus j omega minus e minus j omega. This one's bothering me. I don't know why. I don't know why it's bothering me the way it should. Something happens here. I'm not so sure. Because you know what I'm thinking right now? This is a constant number, right? Because the play variable is z. Understood? So I'm going to do the following because I think I like it when things make sense. R cosine omega naught. Wait, z minus r e to the plus j omega naught. Z minus r e to the minus j omega naught. This is a constant, right? Right? Omega naught is like some value, right? Constants, constants, constants. What does this tell you? If I were to draw my poles, let's just say omega naught is equal to pi over 4. Right? Right? And let's just say I'm just going to throw r is equal to 0.5. Right? Where's this pole? Let's do it right here. Right? The distance between here is 0.5, right? And then the angle is pi over 4. Right? What about this pole? Do a different color. Right here, conjugate or complex conjugates, right? With a distance of 0.5 and an angle of minus pi over 4. right there, right? Draw my unit circle. Use pink. Those are my poles, right? What about my zeros? I have a 0 right here, right? Right? If z is equal to 0, well, this whole thing turns to 0, right? So I have a 0 right here in the middle, right? But what about this guy? Cosine of pi over 4, what's that equal to? Is it square root of 2 over 2? Right? And then square root of 2 over 2, and then multiply by, well, what's r? 1 over 2, right? So that's square root of 2 over 4. But 4, right, is equal to, wait, no, that's equal to 2 squared. That's 2 squared at the bottom. Wait, let me do this math. Square root of 2 over 2 squared, which is equal to 1/2, 2, and then these subtract to give you, I'm going on a tangent, -1, 2, -3 over 2. Is that correct? So where's the 0 over here? It's the 0. What's this equal to? This is 0.707 divided by 4. So the 0 is over here, right? So if I were to punch this in MATLAB, I should see something like this. Does that make sense? Everyone understanding what the Z transforms? Oh, look. Wait. This is my new assignment. This is your old assignment. Do you guys understand why I edit things? Because I want to teach things. I want to make things make sense. 0.9, right? And then pi over 4, right? Right? Understood? This is my old assignment from when I was working with Dr. Steve. You remember this, right? Yeah, you see, you got your education, sir. But Dr. Morris, yeah, we're just keeping it like this, okay? So you guys understand what's going on with lab or computer assignment 6, okay? And then I don't think he tells you to change the R, so this should be a stable system, okay? Are there any questions about that? No? Any final questions before we end the class? All right, have a good day, everybody.